Right, so chapter 19 basically it's called numerics in general, but we were going to deal with three things in this chapter. Solving nonlinear equations, just like those polynomial, those characteristic equations that come from solving an eigenvalue problem, third order, fifth order, depending on how many, the n basically, how many equations by how many unknown you have. So we learn how to solve a general nonlinear equation, right? And then the second part would be about interpolation. If you have a table and you want to interpolate in that table, how you can come up with those values. And the third thing is basically numerical integration, right? If you have a function that you would like to integrate, how do you do numerical integration? So in the first section, 19.1, he starts basically talking about how many digits you should keep. Okay, there is a fixed point system and there is a floating point system that we are interested in. So the floating point is basically, you can write the number just like your calculator, scientific calculator. When you hit the engineering button, you basically see that the digits start moving 3 points or 3 digits, and then you have the number to power 10 to power 3, the number to 10 to power 6, in case you want to say kilowatt or megawatt or gigawatt. So in that system, what he's saying then, what's really important is how many digits, significant digits is in the number. So after the first 0, how many digits you keep? And so in the homework this week, basically, in different problem, I will tell you solve this to 4 significant digits. So I will write it 4s or 5s. Find the solution, and then between brackets 5s. That means that I would like you to find the solution with accuracy down to 5 significant digits. Okay, so if you tell me the solution is 0.2, that's not good enough. You actually have to say the solution is 0.24375, because I said 5 digits. Alright? So he's basically saying, see, this number, this number here or here or here, this would be just 10 to power multiplied by 10 to power 0, or basically multiplied by 1. This would be, multiplied with 10 to power 4. He's basically saying that all those are equivalent when it comes to how many significant digits. They all have basically 5 significant digits, right? Those first zeros doesn't matter. What matters is the 1, 3, 6, 0, 0. Those matters because to the right, not to the left, right? So all those guys have 5 significant digits. Okay. So again, if I say an equation and I would like to find the solution, I said find the solution within 5 significant digits, you would say it's 1, 3, 6, 0, 0. Of course, you make sure that those 0, 0 are correct. You don't just add zeros to make it 5 significant digits, right? They need to really be part of the solution. And then you talk about the round of error. And when we say 22 over 7, or say 7 over 3, no, not 7 over 3. Well, when you keep it like this, like a fraction, this is a number, but it's accurate. But then when you start basically putting the number on the calculator and getting 0.666666, and then you decide, well, I'm not going to write forever, let me just cut here, and you write 5 digits. This is a round of error. And so this can actually introduce a lot of errors when you are doing computation. Alright? Okay. So now after this introduction, we go to 19.2. That's the solution of equation basically by iteration. Solving nonlinear equation by iteration. So here is an example of nonlinear equation. Why this equation is nonlinear? X to power 3, right? And e to power minus x and the sine x, all those are basically nonlinear terms. Right? So solving this equation means what is the x that will make the left hand side equal to the right hand side? What's x value that will make this equal to 0? That is the solution. Right? So when we look at this and say, well, this is a function, forget about the right hand side, forget that it's equal to 0. This is f of x, and this equation can be written as f of x equal to 0. And so this f of x, that's function of x. And you can plot this f of x at any x. Your calculator, if you have a graphic calculator, you can basically give him this x cubed plus sine x plus 5 e to the power minus x, and you tell him, well, plot this for me. So sometimes it's negative, sometimes it's plus, and at one particular x, it will be 0. That's the solution for this equation. So this is the first way to solve a nonlinear equation. Plot the function and look when it will hit the x-axis. Look for the root. That's the easiest way. Just plot it. Alright? And sometimes it's hard to plot the equation exactly, but here is a trick. You can plot the equation at the limit. You are looking for the very small error. Sorry, the very small solution. I mean, it could have a solution x equal 50, but you want the solution that's basically less than 1. So the solution that's less than 1, your application, you're looking for something, and the solution should be from 0 to 1. That's what's the problem requires, not the big one. Then you can look over here and say, well, for very small x less than smaller than 1, I bet x cubed would be bigger or smaller than x. And then you can cancel this with respect to that. And then you would be plotting a simplified version of the equation, right? Which is easier to plot, especially if you remember how does x cubed look like, how does x look like, how does sine x look like. Then you can plot that approximated function easily, on paper even, and you can guess what is the solution is, or where's the first, like a smart guess or a smart iteration. Alright, so we are not going to talk about how to plot this graphically. Let's talk about the fixed iteration point, fixed point iteration. So this method is basically go like this. This f of x equal to 0 that you are looking for a solution for, is there is a way you can plot it, or you can rewrite this equation as x equals g of x. So out of all the x's that's here, just bring one of them to one side and leave everything else on the other side. Let's take this one, for example. Here, there is an x. But you can take any one of them and just isolate this on one side and let everything else on the other side. This will be x equals g of x. Okay? So, for example, let's take this. If we take this guy to one side, here is x, put everything else on the other side, this guy become minus x cubed, this guy become minus sine x, and this guy become minus 5e to minus x. See, I put everything on the other side. What are we trying to find out? We are trying to find the solution for this equation. Or we are trying to find the x that will make f of x equal to 0. But now when we cast the equation like this, x equals g of x, what x are we looking for? We are looking for x that will make this equal to this, right? In that form, we are looking for an equation that will make the left hand side equal to the right hand side. Because again, bring gx on the other side, if it will, the equation become x minus gx equal to 0, or f of x equal to 0. So of course, if x equals g of x, that will make f of x equal to 0, right? So the solution now is that x equals g of x. So your dream is that you substitute x here in this function, x equal 0.2. So that means minus 0.2 to the power 3 minus sine 0.2 minus 5 e to the power minus 0.2. And after you punch the numbers in the calculator, your dream is you get 0.2. The number you substitute is also the number that you get in the calculator. So x equals g of x. That make f of x equal to 0. You found the root that you're looking for. Right? So eventually you want to get to that point when you put the x on this function and you also get this. Okay? But this will not happen immediately unless you actually know the solution. But what you do is that you have an initial guess. You think, well, maybe it's 1. Maybe it's 1. So you substitute 1 over here. That's your x of n. That's your first iteration. That's your first guess. And what you are calculating is xn plus 1. That's the best, a better guess, an improved guess. And you get this number and you put it again, you get this number, you put it again and again, and then eventually you put 0.2 and you get 0.2, or you get 0.2156 and you get 0.2156, and you say, I'm done within 4 digits, 4 significant digits, I'm done. Okay, so the method is simply this: the x is equal g of x, okay, and you iterate until you converge. Will you always converge? No, not always. We'll see why in a second. But basically, fixed point iteration method. All right. So when you see an equation being solved by basically substituting in the equation, and getting the number and then putting it again and again and again, this is called fixed point iteration method. So here is the example. So solve x squared minus 3x plus 1 equals 0. Of course, you know how to do this, right? By this is second order. You don't really need to do all those iterative method, right? You can just say x is minus p plus or minus p squared minus 4ac over 2a. But this is just an example, you know, so that you can come up with a solution that you can actually compare it to the exact solution that you know from the formula. Okay, so how we can write the equation in the form, this f of x, sorry, the function, how you can write in the form that it's x equal g of x. Well, you have two choices. You can get this x out or you can get this x out. Maybe it's easier to get this one. So you get this x out. That means that you put it here. So it will become x squared plus 1 equals 3x. X squared plus 1 equals 3x. Or simply x squared plus 1 over 3 equals x. So x on one side, everything else on the other side. Okay? This is xn plus 1, this is xn. This is where we put the initial guess. This is what we will calculate is the xn plus 1. The improved guess that we will use and reuse and reuse. So he start with, so in that formula, he start with x equal 1. So 1 squared plus 1 over 3. That's 2 over 3. That's 0.667. Okay? So that's xn plus 1. He move it over here. This is basically what I'm going to use next time. So now I have 0.667 squared plus 1 over 3. You do this in the calculator, you get 0.481. You got it? You move it here and you keep running this number until eventually you put 0.3819 and you get 0.3819. The method converged within 4 significant digits. So if the problem said find the solution, solve this within 4 significant digits, you are done. You get 4 digits to basically repeat themselves, you are done. So you could actually, you know, sometimes same formula, but if you start with the wrong guess, by wrong I mean a little bit far away from the root, we'll see where we start that will throw us away. But here he starts with 3, he gets 3.3, he tries 3.3, he gets 4, he tries 4, he gets 5.7, he tries 5.7, he gets 11.4, and you see the trend, right? He's going to infinity basically. So same formula with some guess converge, and with other we call it what? Diverge. The solution is diverging, not converging. He's not going to the right place. He's getting farther and farther away every single step. And so you can basically with your eye you can see what I'm getting farther and farther. There's no point. Keep going, Every 2 iterations they are getting farther away from each other. You have a question?
It seems like the only possible guess is something less than 1 because if you have a power like that, because as you square or cube a power or a number that's greater than 1 is going to grow, and if it's less than 1 it's going to shrink.
And you had your eye. You had your, what's your name again? Remind me.
Oh, Jason.
Jason is basically had his eye on the right place. Okay. So and there is actually an expression, a mathematical expression that will exactly tell you why it's diverging. And you are right, it has to do with the power and whether they are getting bigger or getting smaller. We'll see this in a second. We'll see it. Just wait for a few slides. You'll get it. So again, what is this method called? Fixed point iteration. I'm asking because in one of the 5 homework problem, he basically tell you that program that you will use, which method he's using. So you need to know their name, so that basically tell him, well, this is fixed point iteration or method, or this is NewtonRaphson method, or this is second method. Okay, those are the methods that we're going to deal with today. Right? This is exactly the same example, but it's just written much cleaner. And here at 1, you can see he's basically converging, and at 3 is diverging. Okay? Question so far? So I told you you have multiple choices of getting x, huh? The first, before here, we got this x. Well, maybe we can get this x. We can get this x on one side isolated, okay? Like this, for example, you basically, well, let me send everything else on the other side. So minus 3x plus 1, they go over here, they become 3x minus 1. And this x squared, well, let me divide over x, one of them. So it becomes 3x minus 1 over x, or simply 3 minus 1 over x. So this equation now is written in terms of x equal g of x. X on one side, everything else on the other side. Okay? This is the formula where we put our initial guess. He starts with 3. The same 3 that we diverged last time with the previous formula. Now you put 3 here, and you got 3 minus 1 over 3 is 2.667. You try again and again and again, and you will find out very quickly that it converges. 2618. So again, if the solution said find this within 4 significant digits, you are done. Here's your 4 significant digits, 2618. You put them, you get them. You're done. Okay? And so here is a nicer version of the same slide. Alright? And you can see basic converge whether you start with 1 or you start with 3. So what is the secret? Why sometimes they converge and sometimes they don't converge? So graphically, that's what happens. Alright? This is graphically what's going on. So remember, we put our equation in terms of x equals g of x, and our hope is that the left hand side equals the right hand side. When we put our hand on the root, on the solution, the x should be equal to g of x. So let's imagine this is g of x. We can actually write g of x in different form, right? Depending on which x we are going to pull from the function. So let's call this is g1x and this is g2x. This is the x squared thing, and this is the 1 over x. Alright? And what is that 45-degree line? That's simply f of x equal x. F of x equal x. 45 degree. And so the root that you guys are looking for is when those 2 points meet. That's the, what's it? 2.618? That's the 2.618. And this is what, 0.3819? That's the 0.3819. Those are the two roots. They are still two roots for whatever the formula you are using. They are still the two roots, right? The fact that you wrote g of x in different way, you pull the wrong x or the right x, doesn't change the root. The roots are there. But so why we don't go to them when we iterate on the formula? Well, how does the iteration work? So you put x in the g of x, and the result you take it again into x, as you knew x, and you put again gx. So graphically, this is what happens. So you start with x equals 3. What do? You substitute in g of x, meaning you put it in g of x and you're trying to find the solution or the value of g of x. So finding the value of g of x and then say that's my new x, it's as if you're going horizontally on that 45 degree. and this is the new root, this is x1, and the process is repeated again at this x1. This is x0, this is x1. You put it here, or basically try to find out what is gx corresponding to this new number. And once you find this value, and now it's, well, before it was 6, now it's 11 or whatever, you basically now put it again in 45 degree, and you can see that this guy is diverging. While over here, when we started with 1, it went like this, like this, like this, and you can see that eventually he's going there. So why at 3 we diverge and why at 1 we converge? It has to do with the slope of g of x with that 45 degree line. If the slope is bigger, the iteration will go to infinity. But if the slope, and by the slope I mean the angle of the tangent. So a 45 degree line has a slope of basically 1. And if you are higher than 1, you will show up like this. And if you are smaller than 1, you will show up like this. It's like a horizontal line. Horizontal line will have a slope of 0. So between 0 and 45 degree, that's less than 1. You go higher, and that's higher than 1. It's the angle basically of the tangent. So if the function is basically smaller, it will converge. If the slope is higher than 1, it will diverge. And that's why when we casted this equation in the new formula, the 3, 1 minus x, you can guess basically that the slope is smaller than 1. And so that's why when we started at 3, we converge it to this guy. And when you started to 1, you would also converge over here. Questions? So you can basically, so the formula is that the slope of g of x, how do you find the slope? It's the derivative of g of x. You differentiate this with respect to x. So say g of x is x squared plus 1 over 3, or x squared over 3 plus 1 over 3. What's g prime of x? What's the derivative of g of x? Here is g of x. What's the first derivative? It will be 2x, right? 2x plus 0, right? 2x over 3 plus 0, right? 2x over 3 plus 0. So 2x over 3. So it's this guy, This is the g prime of x. That's the slope. So if the magnitude of this guy is less than 1, it will converge. If it's bigger than 1, it will diverge. And so that's why Jason basically said, well, obviously if you put a number bigger than 1, it will diverge, because the slope is x multiplied by numbers, but it's really x. So if x is bigger than 1, yes, the slope will be bigger than 1. And if x is a small fraction, the slope would be less than 1, and it will converge. Alright? So what is the lesson? The lesson is that if you want this thing to converge, when you are trying to pull one of those x's, just look at this thing and make sure that the slope or the derivative of this function is less than 1 in the area where you are looking for the roots. Okay? Very good. So again, he's repeating that the conversion of that fixed point iteration depend on the slope of g prime of x. It needs to be less than 1 so that it will converge. Alright? And so he's basically showing here another example where the function is x cubed plus x minus 1, and he's basically saying, you know, when you make it like this, when you bring this x over here and become 1 over x plus cube, and then he tried to differentiate it to get the slope, then there is a reason why he said that the magnitude of g prime of x need to be less than 1, because it doesn't matter whether it's plus or minus. The point is the value. It needs to be between 0 to 1 or from 0 to minus 1. It will converge. So minus 0.5 also will converge. Alright? It's just that when the function, here is a, so if we open this a little bit. So this is again the line of just x. And this is g of x. It happened to have a negative slope, because not only, so this is 0, this is 1, and this we are getting more than 1 to infinity, and then you start getting negative, right? Negative slope. So basically with negative slope but still less than 1, he will converge. It's just the conversion, you can see that is basically, it's not monatomic conversion. It's not like 0.3, 0.31, 0.3115, 0.311157, and then he's done. He's like 0.7, 0.6. 0.7, 0.6, and then 0.7. No, let's do it the other way. So 0.5, 1.5, and then he go to 0.6, and then 1.3, and then he go 0.9, and then 1.1, and then eventually he nailed basically the root as 1. So he's coming to the root, but he's coming from both direction. But he's converging. Okay? Right? So again, geometrically speaking, it has to do with the slope of this function. The magnitude of the slope. Right? It just need to be like almost horizontal. If it's horizontal, perfect. You know? But it's like at 45 degree, it will basically just give you this is the limit. It will start going higher than this, it will diverge from you. Alright, so let's move to the second method. So the second method is called NewtonRaphson method, okay, or basically people just call it Newton method. But since my undergrad I still remember as NewtonRaphson, so I'll just keep saying NewtonRaphson. Alright, but you are free to call it Newton. So the NewtonRaphson method is basically much easier, much faster. Okay, why? Because it actually calculates the slope of the function. It approximates the function as its tangent. So that's what makes it much faster. Right? So here's a function, for example, okay, f of x, and we are looking for the solution. That's this point. And so geometrically speaking, that method is basically saying, you know, that function is pretty close to its tangent. The tangent is a good approximation for this function. So if this function is basically that tangent, then that should be the root. It's not. That's not the root, because the function is not the tangent. But you can see that if you are really very close to the root, that approximation would be better, right? So here, that's not a good approximation, but here it will get really very close to the function. The slope and the function is very close to each other, and so the guess that this method is calculating is pretty close to the root. And this gets better and better as we are getting closer and closer. So the method converges very quickly to the root. Of course, that requires us to calculate or find out what is that tangent. Well, the tangent is f prime of x. So this means that you will actually have to differentiate. And sometimes it's easier to differentiate, okay? But sometimes it's hard to differentiate. So I would like you this week, in preparation for the quiz next week, to basically remember what is the derivative of cosine x, sine x, ln x, e to power x. All those preliminary stuff, they may show up in the quiz next time if I'm telling you use NewtonRaphson method. So that function, you know, whether it's cosine x or sine x or ln x or e to power x or worse, you know, ln ax plus p or e to power ax plus p or cosine ax plus p, the whole thing cosine. All those functions, you know, if they are there in the function, the first step is to get f of prime of x. So you have to differentiate those guys. Alright? So just try to remember them before next week. Alright. So we will get the f prime of x. Alright? And so f of x is x cubed plus 3x plus 5. Well, f prime of x will be a smaller version of this. You differentiate. And so you can see that out of this triangle, the slope is tan this angle. The slope, which is f prime at this point, xn, the slope is tan beta. Well, what's tan beta? It's this over this, right? The tan is the length in front of you next to the length divided by the length next to you. So what is this guy? That's fxn. And what is that guy? That's the difference between the two guesses, x0 and x1, or xn and xn minus 1. And this is the formula. This is where it comes from. You don't have to remember where it comes from, because it's already written in your book and the exam is open textbook. But this is where it came from. It's simply that triangle, right? And realizing that the tan is this over this, and we have the tan because it's f prime. Okay, so now what are we looking for? It's xn plus 1. So you put it on one side, you put everything else on the other side, you will get this. Or simply written nicely, it's this. So xn plus 1 is xn minus fxn over f prime xn. So simply, this method basically say that you have to have two columns now. Before the fixed iteration, we just have x and g of x, right? Now we have x, f of x, f prime of x. What do we do with those things? We say that xn plus 1 is xn minus f of x over f prime of x. And that will give us our new guess. And what do we do with the new guess? We put it again and again and again until the function basically just converge. Right? And so graphically, this is what happened. You basically go from this x0 to x1 to x2 to x and so on. Alright? So this method near the root goes like this. Pretty quick. Right? And so a computer program running this method is simply just a loop over that formula. Just calculate the xn plus 1 from this formula, go again and calculate and calculate and calculate. Right? And maybe you just have to put the maximum number of iteration. So that basically if he starts to diverge, you tell him no, just do 10,000 times and that's it. I don't want you to go more than 10,000 iteration. That's enough, for example. Alright? So here is an example. So basically said, well, let's solve this equation. X squared minus c equals 0. That c can be any constant. Right? This is actually a way to calculate. He's saying that this is a way to calculate the square root of any number. So if say the computer wanna calculate the square root of 7, he doesn't know what is the square root of 7. Maybe that's the way he can calculate the square root of 7. Right? So how does this method work again? You have f of x equal x squared minus c. You have to get f prime of x. So what's x prime? F prime? 2x, right? Minus 0. 2x plus 0. So you got f of x, you got f prime of x, and here is the formula. xn plus 1 is xn f of x divided by f prime. Right? And so this formula goes on and on and on until the number converge. So he tried for c equal 2, so c can be any number, remember? So he tried for x c equal 2 and he get the square root of 2. Okay?